Okay, so today this is the second example in the classwork, and it's the question on bacteria growth. Let's read the question. It is the second example. So, bacteria in a lab culture grows in such a way that the rate of change of bacteria is directly proportional. Already we have words, keywords, important to us. Instantaneous rate of change, that is the whole point of our course. That's going to be something like dB over dt. And what that is, it's directly proportional. That means that our constant, our proportionality constant K, is going to be directly proportional to the number of bacteria present, B. And then our initial condition, suppose there are 3 million bacteria initially. So this is our initial condition. And then it doubles every 3 hours. So we're going to write and solve a differential equation that describes the relationship. That means that we start with dB over dt is equal to kb. We start with this. Then we separate our variables, take e to both sides, and then we're going to end up having an equation, b is equal to some initial value e to the kt. But we have an initial value. Our initial value is 3 million. I'm just going to abbreviate 3 million instead of writing out 6 zeros. I'm just going to abbreviate it as 3, and then e to the kt. If we need to, we have too many variables in here. We have 3 variables. Let's use the fact that the bacteria is it's going to double in 3 hours. So instead of 3 million, it's going to go to 6 million in 3 hours. Here's where our 3 is. T is equal to 3. Here's T right here. Watch out, cat. Okay, use your good algebra skills, divide both sides by 3. And then take the log of both sides, ln. We're going to get ln of 2 is equal to 3k ln of e, which is going to go to 1. And then our k value, if we divide both sides by 3, is going to be ln of 2 over 3, which is equal to k. It's also equal to the decimal 2310. Okay, that's good. What is this? This means that our differential equation, when it's solved, is b is equal to 3 and then 0.2310 t. This is our differential equation. So this is part A, done. How much bacteria will be present in 1 full day? In 1 full day, that means that's going to be 24 hours. So if we plug in 24 for this t, we have b is equal to 3e. I'm going to use this constant instead, ln of 2 over 3 times 24. Because I'm going to get 3e to the, 8 ln of 2. Then I'm going to get 768 million in 24 hours. That's how much bacteria is going to be in there. All right, next part. How long will it take the population to grow from 1 billion to 2 billion? One of the things that we have to note right now, here's our equation. Let's see. I'll just rewrite it. Our equation is b is equal to 3e to the 0.2310 t. Now, how long is it going to take to go from 1 billion, and remember, 1 billion is equal to 1,000 million. So we want to see how long it's going to take to get to 1,000 million if we start out with 3 million. And now we're going to use some more algebra skills. Now I have to take the log of both sides, ln. ln of 1,000 over 3 is equal to 0.2310 t ln of e, which is going to go to 1. And then I'm going to divide both sides by 0.2310. 310. All right. This is going to turn out to be, let's see, for 1,025. This, if I punch it into a calculator, it's going to be 25.1478 hours. 4 decimal places, truncated because that's AP standard. That's to get to 1,000 million or 1 billion. Now let's see how long it would take for us to get to 2,000. Because we want to get to 2 million. 2,000 is equal to, we're going to do the same process. Yep. 3e to the 0.2310t. We're going to do 2,000 divided by 3 is equal to e 0.2310t. And we're going to take the ln of both sides, ln, and we're going to get ln of 2,000 over 3 is equal to 0.2310t. ln of e, which is going to go to 1. And then divide both sides by our k value. And then in the end, we're going to get 28.1484 hours. So how long will it take to get from this amount of time to this amount of time? It's going to be 28. The change in time is going to be 28 minus 25, which is about 3 hours. Yikes. Finally, the last one says, why isn't the world inundated with bacteria? Well, I'm not an expert, but there's lots of different types of bacteria. Some of them are really bad, and then some bacteria they don't have a very long lifespan, but you can tell me this answer. I'm just going to do the math. Okay.